Now that you've seen some ways in which two or more methods can be used in concert, here are some common ways that hero methods are combined in practice. The idea of this section is to provide you with template answers that can directly be used in some cases. More importantly, knowing why these came together will better inform your choices when developing your model architecture. Let's discuss a common pattern where you combine simulation, optimization, and learning. This can be applied in situations where the solution space and the problem space are not the same. Take design as an example. Design configurations are obtained from the solution space, and the design objective, the criteria that needs to be met, or the goal it's attempting to accomplish, lives in the problem space. The problem space generally is characterized by more dimensions and is sometimes thought of as the combination of the solution space and an environment space. Training and optimization of a learning model involves iteratively adjusting your solution for each iteration to meet an objective. Both of these tasks are not straightforward if part of the problem space lies outside the solution space. For one, the model doesn't know how a particular set of solutions performed, and two, as a result, it won't know how to traverse the solution space, aka where to look for a better solution. If you have data on solution configurations, environment parameters, and performance of each solution, you can pre-train a model between solution and problem objectives based upon certain environmental conditions. You could then use this model to estimate the design objective for every solution configuration the solving process encounters. If you're looking to maximize this objective, you're left with a two-step process, each run in a loop for every iteration. Step 1, find a set of candidate solutions. Step 2, estimate objective value for each candidate using the pre-trained learner, and adjust search path and neighborhood based on this. If the objective value is getting bigger, stay and search in the neighborhood. If not, jump to a different part of the solution space. So what happens if you don't have the data? One way is to measure and capture data in the real world. However, this may not be feasible for many problems. There may be too many solutions, with each one taking too long or too much to measure. Another approach is to simulate the performance of your solutions for different environments and capture data this way. Note that every time you change your solution, the data you capture will be different. Use this data to teach a surrogate model that estimates your objective for different potential solutions or environments. This approach involves 3 steps that are run in a loop for every iteration. Step 1, optimize, picking the best or many of the top solutions. Step 2, simulate. Use the solutions from step 1 to simulate system performance for different environmental factors. Step 3, learn. Once you have enough data, teach a learning surrogate model that replaces the simulation or alternatively advises on the best simulations to run. Use that model to determine search direction and iterate back to step 1. The 3 steps are used in a cycle to continually narrow down and improve the quality of a complex solution in a multidimensional problem space. This is regularly used in generative design in cases where surrogate learners are tasked with reducing computational cost in engineering design, as later covered in use case number 2. Here is a thought experiment. What if you need to introduce complex multidimensional constraints? If so, now you're left with a problem space, a solution space, and a constraint space. If the solution needs to meet regulatory requirements, the constraint space may be thought of as a combination of the solution space and the regulation space, and may be different from the problem space. How does the process of solving change then? Use the above thinking to expand it. The approach of combining learners, optimizers, and simulators may be used in parameter selection while training complex hero models. Mathematical processes that solve complex problems, such as evolutionary algorithms, oftentimes include parameters that influence how they work. All other things being equal, changing these parameter values results in different solutions to your problem. At that point, performance metrics may be used to figure out which of these solutions are right for the problem, and by extension, which parameter sets. In some problem spaces like neural network learning, the relationship between parameter set and performance metrics may in themselves be treated as a complex data-driven problem. Data-driven because you'll have data on parameter set versus performance metric. You can choose to simulate, optimize, or learn this to see how well the neural network is encoded. Kato AI.